We want to create a state variable model for this circuit. Our input, U of t, is this voltage source, and our output, Y of t, is the voltage across this resistor R2. Now, in order to create a state space model, we need to define our state variables. The choice of state variables isn't unique. There are a wide variety of different things I can choose for state variables, but no matter what I choose, it has to describe the energy stored in all of the energy storage elements in the circuit. We know that capacitors store energy as voltage, so it's sort of natural to choose a state variable as the voltage across the capacitor. I'll call that x1. Inductors store energy as current, so it's natural also to choose a state variable as the current through the inductor. I'll call that x2. Another thing that will probably help me a little bit later on is to define the current through the capacitor and the voltage across the inductor. If the voltage across the capacitor is x1, the current through the capacitor is C times the derivative of x1 with respect to time, so C x1 dot, where the over dot indicates differentiation with respect to time. The voltage across the inductor is L times the derivative of its current, so this voltage is L times x2 dot. Notice that I've defined currents entering the positive voltage terminal, so my passive sign convention is satisfied, and I no longer have to remember the voltage-current relationships for capacitors and inductors. This will let me focus on actually writing the state equations later on and putting them in matrix form. If I call this node here node A, I can write an equation by applying KCL at A. The sum of the currents entering the node has to equal the sum of the currents leaving the node. So the current entering the node is this voltage, U of t, minus this voltage, which is just x1, divided by R1. Currents leaving are the current through the capacitor, which is just C x1 dot, plus the current through the inductor, which is just x2. I can solve this for x1 dot to get a state equation. So this is U over R1C minus x1 over R1C minus 1 over C times x2. There's my first state equation. Since I have two state variables, I need two state equations. Let's try doing KVL around this loop to get our second state equation. KVL around here says minus x1, the voltage across the capacitor, plus the voltage across the inductor, which is L x2 dot, plus the voltage across this resistor, which is the resistance times the current. If I do KCL up here, that tells me this current is also x2, so the voltage across this resistor is R2 times x2. That brings me back to my starting point, so that sums to 0. Solving for x2 dot is 1 over L times x1 minus R2 over L times x2. There's my second state equation. Now, it's typical to put these equations in matrix form. The standard form is a column vector of the derivative of the states. So x1 dot, x2 dot. For a second order system with two energy storage elements, there will be a 2 by 2 matrix here, multiplied by the states themselves, which are x1 and x2, plus a column vector times the input u. The first equation for x1 dot is u times 1 over r1 times c minus 1 over r1 times c times x1 minus 1 over c times x2. So this is a typical matrix operation. x1 dot is equal to this times x1 plus this times x2 plus this times u. My second equation is x2 dot is equal to 1 over L times x1 minus R2 over L times x2. There's no u term, so I can multiply by a 0 to get that. So 1 over L1 times x1 minus R2 over L times x2 plus 0 times u. This is my A matrix, and this is going to be my B vector. Now we need to write our output equation. I don't need this stuff anymore, so I'll make a little room for myself. My output equation in matrix form is going to be y is equal to some row vector with two elements times the states, x1 and x2, plus some number times u. The equation, y of t, we've already decided the voltage across this resistor is R2 times x2. which is just 0 times x1 plus r2 times x2 plus 0 times u. So 0 times x1, r2 times x2, and 0 times u. So this is my c vector, and this d is equal to 0. To do my MATLAB simulations, I need values for R1, R2, L, and C. I'm going to choose R1 is equal to 10 ohms, R2 is equal to 100 ohms, C is equal to 5 microfarads, and L is equal to 1 millihenry. Now let's go put all this information into MATLAB and have it plot the step response. To do my MATLAB work, I'm probably going to want to create a script file. I can put all my commands in the script file and save the script file so if later I want to get it back or modify it or check for an error, it's available to me. If I worked strictly at the command window, once I close this session of MATLAB, that work is essentially lost. So the first thing I'm going to do is change my current working folder to one where I can find my work later. So if I click on this Browse button, I can go to the C drive. In my TIM folder, I think I'll create a folder named SSM_demos. Double click on that, selecting it. That is now my current working folder. By default, whatever I do will be saved there. To create a script file, I can either click on this new button here, or I can just type edit and the file name. I'll call this ex_1. MATLAB's editor opens up and I can just type the commands as I would at the MATLAB command prompt. First I'm going to set my values. R1 is equal to 10. A semicolon suppresses the results of that command so I don't have to see it scroll by in the command window when I run my script file. R2 is equal to 100. C is equal to 5 times 10 to the minus 6th farads, and L is equal to 1 times 10 to the minus 3rd henries. Now I'll define my A matrix. So A is equal to an open square bracket indicates that I'm starting to define an array. The first element is -1 over R1 times C. Spaces separate columns, so the second column in the first row is going to be -1 over C. A semicolon moves me down to the next row, so the second row, the first element is 1 over L. A space will separate the next column over, that's minus R2 over L. That's the end of my array. I'm going to put a semicolon there to suppress display. B is a column vector, so that is also an array. The first element is 1 over R1 times C. The next row down is 0. C is a row vector. Its elements are 0 and R2. And D is equal to 0. Now to create a step response, I can just use the step command. Step of A, comma, B, comma, C, comma, D. That will calculate the step response and display it as a figure in the window. To save the file, just click on the Save button. To run it, go back to the command window and type the file name, ex_1. And there's my step response. Now this is a second order system because it has 2 energy storage elements, but I'm not seeing any overshoot. So I'm thinking the system is probably either overdamped or critically damped. I can check by looking at the eigenvalues of the A matrix. The eigenvalues of the A matrix are simply the roots of the characteristic polynomial. If this is an overdamped system, they are going to be exponentials, not complex exponentials. So MATLAB's eigenvalue command, EIG of A, tells me that these are both purely real, which means the system is overdamped. Now let's change our resistance values and make this system underdamped and see what the effect of that is. I'm going to make R1 100 ohms and R2 equal to 0.1 ohms. Notice that since this is in a script file, it's easy for me to go back and modify it and then just save the file and rerun it from the command window. Now our system has the oscillations associated with an underdamped system. We can check the eigenvalues, which should now be complex, and they are. So the system's natural response is governed by complex exponentials, which indicates sinusoidal signals.